So this building performance session is one of 5 sessions that CIAT Scotland East Knowledge Exchange series are running. We launched our KE series in March of this year and have delivered 9 events in the early career AT and the retrofit sessions, and we have many more to come for both of those 2 sessions. So we'll be launching our mass timber session on the 12th of August and our building modelling session on the 16th of September. So we are very pleased to welcome Building Test Solutions to open and kick off our building performance session, which, like the other 4 sessions in our series, will be running in parallel together over the next several months. So I'm proud to welcome 2 speakers from Build Test Solutions. This is an organisation with deep and strong ties to the architectural technology community and have a strong academic background in applied science, R&D, building physics, and things like that. So amongst other building performance tools and services, Build Test Solutions have pioneered the Pulse technology for air tightness testing. So sharing their knowledge with us today is Dr. Richard Jack, Product Manager at Build Test Solutions, and he'll be describing the science and data-driven method behind building performance evaluation and the vital role of air permeability in energy efficiency. Then we'll have Luke Smith, Managing Director at Building Test Solutions, and he will introduce the Pulse technology with comparisons to the blower door method and how Pulse technology can support optimization of new build designs and add value to evaluation of energy efficiency retrofit projects. Okay, so that's enough of an intro from me. Richard, if you're ready, please steal the screen and start sharing and kick off when you're ready.
Excellent, thanks John. Hopefully I'm wired for sound correctly. Minimize that and maximize that. Okay, so I'm going to give you a bit of an introduction to Build Test Solutions, what we're all about, and also why we're all about it. So we're a company that manufacture building performance measurement tools, and we do that by working with universities and research organizations to find the latest innovations in the research field and then bring them through to commercial products and make them available to people in the field. What we're trying to do is make measurement mainstream. So we've got a target of measuring the performance of 5 million buildings by 2030. And to achieve that, we need a lot of people to start measuring building performance. So here's a sort of indication of that journey that we're going through, taking those new products on the left-hand side, working through basic research, applied research, product development. So for each of our products, we put a lot of time and effort into validating their accuracy and performance. And after we've been through that stage, releasing them for general use. And we'll talk in more detail about Pulse, which is probably our most developed product. So Luke will move on to that at the end. So our mission is to make building performance measurement mainstream. So what is building performance measurement? So there's quite a few different terms that people use for the sort of general field. So building performance evaluation, post-occupancy evaluation, monitoring and verification, measurement, monitoring, testing, and building use surveys. So they all involve going to site and measuring the performance of buildings and varying degrees of invasiveness and different techniques available. But the real key is taking a building and measuring how it really works in practice. So a lot of regulations and guidelines are based upon the designed and expected performance of buildings. That's usually calculated by taking factory measured elemental performance. So what this is going to the whole system of the building and measuring how well it performs. So why are we so passionate about measuring the performance of buildings? Well, I think a lot of the audience will be familiar with the idea of the performance gap. So there was quite a lot of research. It's been going on, sort of really encouraged in the first place by the oil crisis in the 70s. and then waning in interest as we had gas and didn't need to think about building performance as much. And now, as we really start to focus on the climate emergency and also the health of people inside buildings, there's a renewed focus on measuring building performance. So if we take this example, this is from a report in 2015 produced by Leeds Beckett University. They were looking at the whole building thermal performance, the heat loss coefficient of a sample of 25 buildings, and finding that on average they were 60% worse than the design expectation. So the design expectation is what all the guidelines are based on. It's what all our design work is based on when we think about retrofit. And these 25 buildings were 60% worse on average, with one there 140% worse than the design expectation. So the evidence that we've got is showing that the performance of buildings is not as we expect. Buildings make up about a third of energy use in the UK, and that's pretty typical for a relatively cool country. So they're a really important part of our energy system. And we all spend a lot of time in buildings, so they're an important part of our health as well. So it's really important that we start to understand how buildings are really operating so they can be better managed, retrofitted, designed, built. So the issue with building performance measurement has been that this evidence has come from several academic-led, quite detailed studies of a few buildings, where we're spending thousands and thousands to measure the performance of quite a small sample of buildings. And the tests have been generally quite invasive. So a lot of them need the building to be vacated in order to do the measurement, sometimes for a period of quite a long time, weeks. So what we're trying to do is address the cost and the invasiveness of the measurements. And that's all part of our mission to make measurement mainstream. So here's a little example of why it's a nice idea to measure. This is an estate of houses in South London that I visited a few years ago and measured the performance of 10 of them. They're all built at exactly the same time, pretty poor solid walled properties, but ostensibly all exactly the same. If you measured the overall thermal performance, the heat transfer coefficient if you assessed it via a survey, via an EPC survey, not measure, assess, a visual survey, they would all come out at the same number. But now we've got these 10 identical houses in this graph in the bottom right hand side, and you can see that their actual thermal performance is varying massively. So even if you've got buildings that are seemingly identical, the actual thermal performance is varying quite widely. And that can be for a number of reasons. I mean, for one thing, these houses have been there since the 50s, so they're now 70 years old. So they've had quite a long history. A lot can happen to a building in that time. They'll have various retrofits. Some will have small extensions, porches and things. So there's quite a long life to a building that can change its thermal performance. But even if you measure newly built buildings, you'll find that the performance varies quite widely between what seemingly very similar buildings. And that's because they're a pretty complex system, really. There's quite a few different things that go into the building. They can each go together differently. They're built outside. It's not like we're running things off a factory line, that the buildings are built outside in tough conditions. So there can be quite a lot of variation between them. So to properly know these buildings, our argument is that you really got to go there and measure the thermal performance. Here's another example. This is another block of flats this time, and we measured the thermal performance of almost all of the flats. And you can see that in some cases, in this chart, I'm comparing the estimated heat loss parameter. That's the overall thermal performance divided by the floor area to normalize it for size. So we're comparing the predicted heat loss parameter taken from a SAP survey in orange on the right hand side with the measured value, which is in blue on the left hand side on each of those towers. And you can see that in some cases, this is now per archetype in the flat, the average measured performance for each of them. In some cases, the performance is actually as predicted. In some cases, it's better than predicted, and in some cases, it's quite a lot worse than predicted. So it's again showing that variation, and we're finding the more measurements we do, that especially in existing buildings, it's quite common for the measured performance to be better than the predicted performance. So the whole point about measuring is that it's not just about energy performance. If the performance of your building is different to the prediction, it can have a lot of varied consequences. It doesn't just mean that you could have worse energy performance. It could have impact on thermal comfort of the residents, which is important because if you've, for instance, got poor air tightness, especially in key areas like across a floor, people will get cold even in quite warm temperatures. So the energy performance and the air tightness is really important for thermal comfort. And really, really important is making sure that the building has enough ventilation, enough fresh air to avoid damp and particularly mold. In the last few years, one of the largest killers of people in the UK has been respiratory illnesses, which are really closely linked with having mold in buildings. So it's an incredibly important thing for health. And then quality control is important. You know, if you're buying, you know, for a lot of people, it will be the most valuable asset they ever buy. Wouldn't it be nice to have quality control, to know that the building is as you expect, and noise as well? So the whole message is you can't manage what you don't measure. So you need those measurements to properly understand the building to manage it properly. So this is what I sort of touched on earlier, that measurement isn't always a negative. So you could, as a designer, you could illustrate to clients that your buildings really do perform. The performance gap's pretty well-known phenomenon now. Imagine what a benefit it would be to be saying, look, our buildings really perform, we believe it, we've tested it, we've demonstrated it. Yeah, if we design and implement better retrofit solutions, it's so key to our targets to reduce carbon across the board, but also to address fuel poverty. Yeah, we can properly target and design our retrofits, then we'll make a big impact on the quality of our buildings. And I think a really important part of that is getting things right first time, especially now we're moving on to installing a lot of heat pumps. When you're installing a heat pump, it's incredibly important to its efficiency that it's sized properly for the building. If it's undersized, then you won't have enough heat, which is a problem. If it's oversized, then it won't be running at its maximum efficiency, and the coefficient of performance will be worse, and it will cost more to run the building even though you can get enough heat. So it's not the same as with a boiler where there's not a gas boiler, there's not as much penalty for having an oversized system. And we can also validate the results of what we're investing in. So I think that's really important, quality control. And how do we know what works, what materials work, what processes work, without measuring the performance that we achieve? So that can be in a soft way to understand and get lessons learned for future buildings. But we've already seen with air tightness that we're moving towards harder regulations on building performance. And I think that will be the pattern. We'll start to see that across more factors in building performance. So U values, overall thermal performance. And we're already seeing that there's funding bids that are requiring performance measurement as part of the bid. So this is the performance gap in building regulations. So in the latest consultation on building regulations, the performance gap was mentioned 9 times. So it's really coming into prominence in regulation. That's that harder side of measurement. And we're increasingly seeing local planning restrictions requiring performance measurement. The REBA plan of work has a post-occupancy evaluation step in there. And in PAS 2035 and 2030, we're seeing voluntary standards which are putting an increasing emphasis on performance measurement and delivering what the design has said we expect. So this is another, earlier on I showed a sample of 25 buildings with a 60% difference in the delivered performance, and it seemed a really negative message. So here's another study where we've got around 30 buildings, and this time they're designed specifically to have high performance and with a smaller subsample of passive houses with really tight on-site controls. And in this case, we're delivering an average performance gap of only 20%. And you can see there, there's quite a big variation. Some buildings are better than predicted, and some buildings are still significantly worse. But there's more variation and a tighter agreement with the predicted performance. And in that subsample of passive houses, only 6 in that sample, but that was an average gap of only 5% in the expected and delivered thermal performance. So it is possible to reach those standards. And in passive house, there's long been a culture of looking at the energy performance once it was built, and on-site checks at each stage. So you could see the effect of using those measurements in making sure that we're actually building what we thought we were. So what to measure? So on a sort of actual metrics that you're measuring, there's energy consumption is a really clear metric. How much electricity, gas, oil are we consuming for that building? And then the internal temperature and relative humidity, what conditions are we delivering inside the building for that energy use? But then there's also these intrinsic measurements of building performance. So quite a few of these charts have looked at the heat transfer coefficient. That's the whole building heat loss rate. So that's a rate of energy transfer per degree of temperature difference between inside and outside. And I think of that as the best first health check of whether a building is performing as you expect. And then key is air tightness and ventilation, two different but linked metrics. So air tightness is about how much air is moving into and out of the building through cracks and gaps. And ventilation is how much air we're deliberately adding to the building to make sure we've got enough fresh air inside. So those are sort of metrics you might measure first up as your health check on the building. And then if there is a difference, I think there are several follow-up or investigative steps to follow afterwards. So maybe measuring elemental heat loss, U values, do the walls, floor, roof perform as we expect? Could that be the reason? Is there a difference there which causes the difference in the whole building heat loss rates? Thermal imaging to find particular areas where there's a problem. And then building services monitoring, really key for heat pumps as well. Are we delivering the efficiency that we expect out of the systems? And then moving on more particularly to air tightness, these are 2 houses in which I've lived, which actually have a really similar, quite different houses, but actually with a really similar air tightness. So on the top there is a 1930s semi-detached solid walled house I lived in as a student. Pretty good air tightness, you could say, for that sort of building, but quite poor insulation. But in turn, that meant that the heat loss through air movement and ventilation was quite a small, well, relatively small part of the overall heat loss, only 20%. And then moving on to this house built in 2008. I mean, for a house built in 2008, that's quite poor air tightness. Similar sort of level to that 1930s house, and only just under what the limitation in building regulations is, but quite a well insulated house. So that means that with that level of air tightness, actually the ventilation and air infiltration forms a much larger piece of the overall heat loss. So as the thermal performance of buildings improves, then the air tightness and the ventilation heat losses get more and more significant relatively. And the other side of that is we want to control air movement to reduce heat loss, but we also need to be providing enough fresh air to make sure that we've got the right air quality inside. The general theory on this, and I'll be repeating something that everyone knows like the back of the hand, but is build tight, ventilate right. And the whole point of that is when you have poor air tightness, it's usually not designed in. It's due to maybe construction defects or designs that don't quite work in practice. And that means that the fresh air provision is randomly dispersed around the house instead of being provided to where it needs to be. So it's much more important that we have a deliberate level of air tightness that we're trying to meet, and then providing the fresh air with ventilation. So the key that they go together, that air tightness and ventilation. Yeah, air tightness measurement is really exceedingly rare in existing homes and only on a minimum sample of new builds. Well, I think most sites will be on all buildings now, but I think we're generally testing for compliance rather than thinking about how important it is to provide the right amount of fresh air to the building. So I wanted to go back to the start and just think, why are we measuring air tightness and ventilation? So we do it to understand energy performance and to understand if we've enough ventilation, and those are the reasons we should be doing it. It's been introduced to compliance to force us to think about that, but it's key to go back and understand why we're doing it. It's not just to tick a box, it's to make sure that we've not got excessive heat loss, but we've got enough ventilation to provide a healthy internal environment. And this is kind of an example of what I was saying is, are we testing for the right reasons? So here we've got from the ATMA lodgement statistics. So this is a sample of hundreds of thousands of air tightness measurements across several different ventilation systems. System 1, background ventilators, moving on to System 4, MVHR systems. And these different systems are designed to work with different levels of air tightness. So we know that an MVHR system will only really work in an airtight building, yet the measured air tightness across all those buildings is pretty much the same in every type. So are we testing for the right reasons? Are we testing to make sure that we're going to get the right ventilation system to go with the building, or are we testing to meet the compliance deadline, the compliance limits? So it's really important to think about that. And you know, I've talked to some house builders, and they're saying that you can sort of deliberately design and then go out to construct a really airtight building. And you know, those sort of levels of air tightness, 3, 4 nowadays, aren't too hard to meet, I don't think. How can you deliberately design a house to meet an air tightness of 5? You're saying, well, we're not looking for really high standards, we're just looking for okay standards. Actually, I think by design that's really quite difficult to achieve. So we need to be thinking at design stage, if you're designing for an air tightness of 5, what does that mean for the actual building? How does it go together? I think really it makes a lot more sense to be designing for a good level of air tightness, a lower level, and then providing the ventilation to go with it. It's a bit sort of back to front, I think, to design for an okay air tightness. And then that last point of, are we testing for the right reasons? This was a really interesting paper that came out from Jenny Love at UCL around 5 years ago now. And it was, there's several different air tightness limits, 4, 5, 6, that people are designing to, and look at the percentage of tests which fall immediately before those limits. If you had a sample of tests that were sort of distributed as you'd expect to see a normal distribution here, but instead we've got these huge steps just below the air tightness rate. So what does that mean for the tests? Well, it could mean a lot of things, but it feels a lot like it meant that before the final test was carried out, we went round and gunked up the gaps temporarily to meet the regulations. So we've got to make sure we test for the right reasons. So I've given a bit of a background on BTS, measurement and air tightness, and I'm going to hand over to Luke to talk specifically about pulse.
Brilliant, thank you, Richard. Let me just, brilliant. So yeah, thanks, Richard. So that's hopefully provided a useful background for everyone as to obviously how important and how significant measurement is generally, but also the proportion of which sort of the role that air tightness plays in that overall not only space heating demand and thermal performance role, but also in terms of ventilation and in understanding indoor air quality and that side of things. So yeah, this half of the presentation will now delve into the equipment and the technology available, and let's jump straight into what is only sort of natural in terms of wanting to try and directly compare the two mainstream kind of commercially available solutions, Pulse and the blower door fan. And so there is also tracer gas testing, which is an application of releasing sort of an inert gas into a property and tracking its decay over time, but that requires the property to be vacant, and I think it's fair to say it's fairly it's a useful research tool, but isn't all that practical in testing at scale. And certainly if we start thinking about kind of stipulating it for regulations and things, it wouldn't be very practical at all. So yeah, the two mainstream available technologies, the blower door fan, which you'll all be very aware of, and Pulse is the new kid on the block, as it were. So yeah, we were encouraged to kind of share sort of very openly all the details, including costs here. So Pulse is more expensive on a sort of upfront capital cost basis. At 6,500 for a full system is what you see here. The test duration is typically kind of 10 to 15 minutes. By the time you've fully set up the equipment, done your measurement checks, sealing up, and the actual execution of the test itself is 10 seconds. So that's kind of the 15 minutes is from turning up, opening the front door and packing away, leaving again. The measurement metric, so whilst the two pieces of kit are measuring at very different pressure levels, and so they are serving two different purposes. The actual output metrics are actually common between them. So Pulse is measuring air permeability, so meters cubed of air per meter squared of envelope area per hour. Pulse is measuring that at 4 pascals. The blower door is measuring that at 50. And then you're from that very same measurement, you're also understanding air movement, so quite simply meters cubed per hour, or based on volume, air changes per hour, at that given pressure difference. And then the blower door, the equipment is lower cost, but you're tending to have to require different size fans to suit different applications. So it wouldn't be uncommon to have a mini fan and a mini fan canvas and frame, and then as we've shown here, kind of a system that might house a medium size fan or double stacked medium size or even triple stacked fans. The test duration is then a bit more involved. You're having to set the fan up in a doorway, and it's testing at a much higher pressure range. So the fan must run at a certain speed to overcome unsteady flow, and it forces you into testing at a higher range, which is why currently in the regulations you have the 50 pascals reference pressure level. Let's get into a bit more of the detail behind these methods and the science and various applications. So starting with the blower door test, and as we've touched on, the standard is the result cited at what we refer to as Q50, so 50 pascals. Well established. The fan method's been around since the 70s. It's enshrined in the European Directive for Energy Performance of Buildings. It's been in the UK building regulations since 2007. It's written into Section 6, Section 3 of the Scottish Building Standards. It's slowly ramped over time. So since 2007, it started off sample-based and has gradually ramped, adding penalty to properties whereby you don't test, to the point where now, most, particularly mainstream developers at least, are doing 100% sample testing. I would say that's predominantly to avoid the associated penalties of not testing, rather than necessarily wholly appreciating the value of the test in itself. But we can come on to that in a bit more detail. But it's probably not fair to say it's only done on a sample of buildings. It's increasingly common. And we refer to it as a steady state test. So a bit of a schematic here as to how it's working. The fan is delivering a flow of air across the envelope, either pressurizing or depressurizing, and you're sampling the pressure both inside and out. So you to appreciate kind of what pressure difference is being delivered by a given flow rate via the fan. So quite high airflow exchange between inside and out makes it necessary to record the conditions externally in terms of sort of barometric pressure and temperatures inside and out. And you're taking a series of readings across a range of pressures. And yeah, we're taking a pressure tapping both inside and out. And you plot that flow versus pressure difference to derive the air leakage at a given pressure level. I often describe the fan test as a very useful stress test of the building. So clearly you can pressurize and depressurize by turning the fan around, basically. Depressurizing, you're pulling window seals in, pulling the loft hatch down. Perhaps drawing air in through service penetrations and down through kind of service voids and things. Pressurization, however, you're perhaps pushing window seals out, you're testing those rebates in the other direction, or you're pushing the loft hatch up and testing the latches. And that's extremely useful to be able to push and pull on the building fabric like that at pretty high pressures. So you'd certainly not ever experience a building being subjected at a steady rate like that. These kind of pressure levels, like gusting wind may deliver 20 to 30 pascals at best on kind of the wayward side of the building, perhaps. Obviously, higher rise buildings, you might see quite interesting pressure variations going on, but generally, no building has ever been subjected to sustained levels of pressure or depressure in this way. But it's, like I say, a very useful stress test. That steady pressure hold also allows for diagnostics, so you can either under pressure or depressure. You could go around with a smoke pen or use a thermal imaging camera and identify leaks, which again can be extremely valuable when you're pursuing a certain level of air tightness. Another benefit, a notable benefit of the fan method is that actually these medium or larger fans have a very wide operating window. So that's tended to be what's carried around by an air tightness tester, and it provides good scope for testing, particularly most residential settings. And then there's tends to be read across from the gauge into software to then provide to calculate a result and a certificate. In terms of the downsides of the method, however, it clearly blocks off a doorway. So how often a door, particularly in existing property, can be a significant leakage point, especially with letterboxes and perhaps poor fitting or damaged seals and those kind of things. It's a bit of an inconvenience. So in covering off the doorway, you've people can't necessarily readily come and go. This high pressure, like I say, it exerts an unrealistic pressure on a building. So you're causing those air leakage paths that you're forcing aren't necessarily going to occur in reality. So there's whilst it's a good stress test, there's an argument to say that actually what's the true value of the output of the measurement. It's a building isn't really that leaky under normal conditions. The fan has to run at a certain speed, as I've already touched on, so you can't measure reliably, typically below kind of 20 pascals. Maybe extremely still conditions, you might just about edge down to 15 pascals or so. But that's why the testing range for a fan tends to be 20 through to about 60 pascals, with the results cited at 50. And it's a faff, quite time consuming to set up. Your pressure tappings, internal and external, and it can be quite difficult to mount sort of blower door fans in more complicated doorways or windows with sort of fancy rebates and things. Again, as we push on for increased performance, things like rebates start to get more and more complicated, and quite difficult to mount these systems in those settings. To complement a blower door, or to often sort of used alongside, is certainly best practice is to use a power flow hood. So I just added this slide in as a quick word. It's not an air tightness measurement tool, but it's something else that exists to measure the airflow rate through purpose-provided ventilation. So your fans, or you supply and extract, whether that's intermittent or continuous through the wall or ducted systems. It's mostly used to help balance the system, but also can obviously validate the supply and extract rates. But what again is overlooked here is that a fan test nor a power flow hood has actually provided a measurement of the true background ventilate, or the background infiltration, background air leakage, and obviously all of these fanned mechanical systems, as well as natural ventilation, is being driven by this natural pressure level background infiltration. So to this point, the tools available to us haven't been able to measure that particularly well or very accurately. Many of you will be familiar perhaps with the divide by 20 rule. So this is something that's often applied in our energy models, where a 50 Pascal blower door test is divided by 20 as a kind of a very crude extrapolation down to what we think the infiltration would be at normal, or the leakage would be under normal conditions. But that is a bit of a fudge, a one size fits all factor that's applied to a test, and it's not necessarily representative of reality in any way. So moving on to pulse. As I say, new on the block, it's a compressed air based alternative to the fan method. And its primary USP is the measurement of air leakage directly at 4 pascals. So if you were to sample the pressure difference between inside and out of the building over the course of the seasons, the course of a year, you would the average would be 4 pascals. Of course, you would see the background pressure spike on windy days, gusty days, it would be spiking up and down. But if you were to average it out over the course of the seasons, the typical pressure difference between inside and out is 4 pascals. So Pulse is measuring that air leakage directly at that level. And so I strongly encourage not to draw kind of direct comparisons between Pulse and blower door, because they're both tools that can offer very different things. And so it's only natural to make that direct comparison and to look at the setups and the costs and that side of things. But fundamentally, Pulse is actually a new technology that unlocks and enables the measurement of something completely new, something that we as an industry as a whole just have not previously been able to understand. It's only previously been possible with the tracer gas test, which, as I've touched on, is extremely impractical and time consuming and very expensive. So these air change rates that are measured by Pulse are representative of real world as occupied conditions. Actually, then everything else is a sideline benefit, but it is remarkably simple to set up and use. It's 4 connections, one from the compressor to the air receiver into the controller, a plug in the wall. What you see in that picture is everything you need to go testing. I don't know if you're 4 cables and away you go. It's a completely self-contained unit, so you haven't got anything going through the envelope. And it's not able to do that diagnostics piece, but it's providing that kind of pass-fail or that direct measurement at 4 pascals, which in itself, as we know, is very valuable. And it's low disruption, so you're not blowing a gale into someone's house or sucking the heat out of it, so particularly well suited to occupied homes. The development just earlier this year is that the English and Welsh regulations at least have now accepted Pulse as a means of testing for compliance for new build homes. and also it's accepted under PAS 2035 for retrofit. And we'll come on to this, but it's out for consultation in Scotland at the moment. So yeah, just to elaborate a little bit more on the test process. So the air receiver is placed centrally on the ground floor. The compressor is connected up to the air receiver first and foremost. And the charge time is about 8 minutes. So during that time, you're not faffing around trying to mount the fan in the door. You're actually able to go around and measure up, make sure all your internal doors are open, seal up any purpose-provided ventilation if that's the nature of the test that you're doing, which is common for sort of compliance testing at least. You then input those your envelope area and volume into the control unit, as shown in the picture there, on the controller, and press go, and the button sort of executes the test, which, as I've touched on, takes 10 to 15 seconds to actually run through the test and present the measurement on the screen. Those tests are then saved on the control unit. You plug in a USB stick, you download them, and then just in the bottom right here you can see a screen grab of our dashboard, online dashboard, where basically you can manage projects and save tests, create reports, analyze results, keeps them all centrally in one place. And we're just in the process at the moment of adding lodgement capability direct from here via IATS and hopefully in good time via ATMA as well. So yeah, I think I've gone over most of these, but yeah, the main sort of spirit of sort of the same slide as the fan testing. The main features and benefits of Pulse: you're measuring directly at ambient conditions. You're able to measure the whole building envelope, so you now included the front door. There's no artificial stressing of the building envelope. Very minimal setup, very simple to operate. Immediate feedback and readout of results. It's quite literally a black box test. It's you press go on the controller and voila, you see the results on the screen. And as Richard touched on at the very start, we've put an awful lot of work into the validation, verification of our methods, with extensive field trial testing and third-party verification. And so we can state with confidence that Pulse provides very accurate and highly repeatable results. Pulse cannot identify the leakage paths and doesn't provide that stress test, deep pressure as offered by the fan. One thing we often say in response to the inability to do diagnostics is that there's actually there's a cultural thing there, where whilst the fan is great for diagnostics, it's not ideal that we're turning up to do it as a compliance test right at the end of the build. So at that point, all you can really do if it is leaking a lot is run around with a mastic gun or some expanding foam, which is not a lasting durable fix or a lasting durable air permeability air tightness barrier. So what we encourage is that actually a fan, either a blower door fan and a specialist air tightness testing operator, or indeed our leak checker product, are both well suited for the intermediate kind of testing. So we encourage site teams, developers, contractors, project managers to test throughout the build, check at first fix, moving on into second fix, that primary air barrier is doing what it should, and then actually there's no surprises when you come to the test at the end, the compliance test, the pass fail test that you may well do with Pulse. So yeah, this is our offering to the market, the leak checker, which is a small window mounted fan, quite simply there to help create a deep pressure difference across the envelope. Control it with a mobile phone app, so you can control the fan speed from different parts of the house, and it just allows you to go around with a smoke pen or an IR camera, or even feel leaks with the back of your hand and address them earlier on in the process than waiting to the absolute death. And we retail this at £1,200, so it's cheaper than buying an outright blower door fan system as well. So in terms of, I've mentioned the product validation that we've gone through with Pulse. It's been one hell of a journey. I won't labour all of these bullet points, but basically it's had 15 years of academic development. It was the subject of a PhD with the University of Nottingham, lots of research council grants and work that's gone in. And then BEIS, the Department for Business, Energy and Industrial Strategy, has very kindly sponsored a lot of the field work and allowed us to do third-party verification with BRE, the MPL and Cambridge Architectural Research, and all of that culminated in sort of what we see today with the acceptance of Pulse in the building regulations. But yeah, it's really not trivial stuff. So I estimate it about 2 million spend over the full course of the 15, 20 years or so of development. So this isn't just something that's come into being overnight, and it's not no mean feat. It's not trivial. Conscious of time, so the policy and regulation side of things. So as I said, Pulse accepted under England and Wales new build regs, currently out for consultation. It's question 16 and 17 for new build in Scotland. So yeah, please do voice your support for Pulse if you're responding to that one. England and Wales have not long consulted upon the inclusion of Pulse for non-residential buildings. And as under PAS 2035, which I understand is a UK-wide, Pulse is again permitted within there for testing existing homes. So just thinking about some of the applications, how you as architectural technologists might adopt Pulse or start to think about potential new services or propositions that you could offer with such technology. There is a whole industry around airtightness testing of new build. There's circa 500 to 600 airtightness testers in the country serving that market. But actually we build in the order of 200 to 300,000 homes a year. I know it's often cited, but there are 26 million or more existing homes, and PAS 2035 and Eco 4, when it comes into being, are absolutely driving at increased levels of measurement in the round, but including airtightness and understanding both the air leakage from an energy standpoint, but also what that means for the ventilation needs of a building. So that it's a massive step change from where we are in needing to increase industry-wide capability to measure existing buildings. Both for the energy efficiency and comfort side of things, but also the ventilation and moisture risk side. So there's scope for testing before, during and after works. So you could imagine, even at a level of adding an extension to a home, let's measure the airtightness and the thermal performance of this building prior to doing any work. Let's then inform what we might do about the spec of the extension, and then actually what, if anything, is that extension done to the overall final thermal performance and airtightness, and how is that might have had a bearing on the ventilation needs of the building, right the way through to more conventional retrofit of external wall insulation, increasing the airtightness and thus impacting the ventilation needs and so on. Even if you're not even doing fabric interventions, you could assess the background air change rate of a building purely for the purposes of thinking about ventilation. So if a home is stuffy or people suffering from asthma or those kind of things, you could actually test and intervene purely on that basis. And social housing, of course. So rather than reactively sort of responding to mold and damp call outs, there's huge scope to proactively measure the stock and understand what is airtight, what is not so airtight, is the ventilation provision adequate, is it actually then the residents' behavioural habits that are impacting that mould and condensation, or is actually the property inadequately ventilated, and supporting housing providers in that is a massive opportunity, I think. The new build's an obvious one, so the quantity and rate of homes is only ever on the up. Quality of homes is forever in the spotlight and needing to ramp. as we approach the sharp end of performance and net zero, air tightness really is the quick, easy win when it comes to fabric performance. You're only otherwise adding thickness of insulation and increasing the plot footprint and all of this very complicated stuff. Whereas getting air tightness right and actually designing and delivering on that is an absolute quick win. And yeah, air leakage equals drafts and discomfort, so it's a massive thing on customer satisfaction, health and well-being. So yeah, as we've touched on, it can be used for quality assurance, but also for that post-completion compliance test. And I do think Pulse is better suited for that completion test, provided there's been interim testing to just provide that quick pass-fail. And I, sorry, just jumping back, also on that one, there's the whole ventilation, the sort of the Part F side of things as well. I wouldn't surprise me if increasing levels of testing beyond power flow hoods is gradually introduced under Part F, and we'd like to see Pulse as part of that in terms of assessing background ventilation rates. For some of you in the audience, these specialist applications might be of interest. So we've got a few use cases across these bullets, but huge more that can be done. So looking at Pulse for testing of clean rooms, containment labs, refrigeration chambers, server rooms, data centers with fire suppression systems. There's a whole host of areas. One that's particularly interested me, and we've not yet kind of had time to explore it with anyone, is actually also testing at a room level. So yeah, testing at individual office spaces or classroom level, thinking about kind of COVID risk assessments and that side of things. And yeah, related then, sort of non-domestic applications. Again, something that is a future development area for Pulse, but you can daisy chain air receivers to deliver an even pressure distribution across a large area. So yeah, there's huge scope there as well. And unlike a fan where you would need different size fans to serve different applications, Pulse is all the same kit. You simply extend it by adding air receivers. So I think I've overrun a smidge, but just in summary then, so as Richard's outlined, there's often a gap between anticipated and as-built performance. It's well understood, but it seriously risks undermining millions of investment, as well as kind of the overall national zero carbon goals. It's influenced by a whole host of different factors, but it cannot be stressed enough that no two buildings are ever the same. And yeah, I find it hard to counter the argument for what you can't measure, what you don't measure, you can't manage. As we've shown here with Pulse and some of the other techniques in our portfolio, the tools and techniques absolutely do exist to enable the measurement of true performance, and it's becoming less and less disruptive, more and more affordable, and should absolutely be done at scale. Despite air leakage measurement generally being a more established field, it's been in the regs since 2007. There is so much scope to do so much more, and just overall increase the richness of the tests and the arising data. I think we do currently simply view it as a compliance checkbox, pass fail, are you under 5, are you getting the right number to plug into SAP? There's so much more to it than that. There's so much more value that can be added to a test, whether you're measuring a different pressure level or presenting the results in different ways and implying different required interventions as a result of them. Pulse has been subjected to extensive commercial and academic and third-party validation over 20 years, and yeah, the product's available today, accepted in the UK and hopefully in Scotland very soon. Certainly already under PAS 2035, but hopefully also on the new build. And yeah, I encourage you to all have a very open mind as to the opportunities presented by measurement and Pulse. And I will stop there if that's okay, John.
Brilliant. Thank you very much to both Luke and Richard for joining us today and for sharing their knowledge. and certainly for giving us a deeper insight onto the application and methodology of the building performance evaluations. And also we very much appreciate the critical level of assessment and transparency and the methodologies and approaches that you guys had spoken through today. So thank you to everyone for taking time to join us this afternoon. And as I described at the start, any questions in the chat box will be sent to Luke and Richard, and we'll post the answers on our CIAT Scotland East Region LinkedIn page under the flyer. So we hope that moving the answers and questions onto an online platform will create a repository on the topic and allow the conversation for building performance and architectural technology to expand. So please do reach out to Richard and Luke to continue speaking about your interest in this topic and application of the technology. And thanks again to Build Test Solutions for volunteering their time and supporting this knowledge exchange event. So before we finish up, I just want to mention two upcoming events. One on Thursday, the 12th of August, we're launching the Mass Timber Knowledge Exchange session, where Storo Enzo will be joining us to discuss the types, styles, and things you need to know when designing with mass timber. And on Thursday, the 18th of August, CIAT Scotland East region are collaborating again with CSIC to bring you another knowledge exchange event. And this one is in the mass timber session. This will be a mini conference where speakers from CSIC, Transport Scotland, 360 Architecture, Ecosystems and Building Research Solutions will be presenting their work from the Near Home project, where they used mass timber, CLT, DLT, and NLT to retrofit shopping units with office space to decentralise the workforce and promote growth in smaller towns and villages. So until then, and on behalf of CIAT Scotland East Region, thank you again to both our speakers and Build Test Solutions, and thank you to everyone that joined us, and we hope that you've learned something here today, and we look forward to seeing you at our next event next Thursday.